Okay. All right. So I put together a few slides over basically yesterday, talking about basically what's going on the wire for InfiniBand. And I'm talking about InfiniBand because, RDMA is basically taking the InfiniBand transport and running it over Ethernet. So in order to kind of understand how that works, it makes sense to take a look at what's going on for InfiniBand. Because it's, you're running the same operations with the same packet formats and whatnot. Another thing that I should mention as well, probably everybody on here is already aware of this, but we have a mailing list and a Slack workspace now. So if you're not connected with those yet, there's a link on the slide there you can go take a look at, and it has all the join links on it. All right, so the agenda for this talk that I have, I'm going to take a look at the quick protocol comparison comparing InfiniBand, PCI Express, and Ethernet, because there are some similarities and some differences. If you're familiar with, one or more of these protocols, might be interesting. And kind of the design of the physical layer does have some impact on, how the protocol works. And then I'm going to take a look at IV transport services, transport functions, and just very high level what the packet formats look like, and then how Rocky fits into all of this. All right, so moving on to just a quick comparison of the protocols. So InfiniBand, unlike Ethernet, it's a D-word based protocol. So it's actually quite similar to PCI Express in that route. You might be wondering, why did I put PCI Express on here? Well, if you take a look at the table, it should become pretty clear. InfiniBand and PCI Express share a lot of similarities. So the fact that the protocol is D-word oriented is one of those similarities. Ethernet, you can make the packets any length that you want. For InfiniBand and PCI Express, everything is done in terms of D-words. So, the packet length fields, header length fields, and whatnot are generally in terms of the number of D-words. All the components of the packet need to sit on D-word alignment. The packet payload is actually padded out to D-word alignment before the ICRC. There's a few things about InfiniBand because of the D-word alignment that you don't see on Ethernet, right? With Ethernet, you can make the packets any length you want. The Ethernet CRC or the FCS, that just goes at the end of the packet, wherever that happens to be. So it's a slightly different story. The header size is also another thing to consider as well. For InfiniBand, the MTU, if you will, which is called the PMTU for InfiniBand, it covers the actual data payload, but not any of the headers. For Ethernet, it's the same thing, but you usually have, IP and TCP and UDP headers and whatnot, which from the standpoint of Ethernet are payload data. So if you add an additional, TCP option or something, that actually eats into the amount of payload data that you can send. But for InfiniBand, the thing to keep in mind is that all of these extension headers and whatnot that may or may not be present, this doesn't actually affect the amount of payload data that you can send in the packet. So if your PMQ is 4096 bytes, it doesn't matter if you have no extension headers or a bunch of extension headers, you can always send 4096 bytes of data inside of the packet. Additionally, for InfiniBand and PCI Express, you can send 0 payload if you want. You don't need to pad it out, right? The header alone is perfectly fine. For Ethernet, you got to pad it out to 64 bytes. InfiniBand and PCI Express also support, virtual channels and traffic classes natively. There's actually fields in the packet headers for this. For Ethernet, you could say, yeah, PFC supports traffic classes, which is true, but the underlying wire protocol doesn't, because there's no fields in any of the packets to indicate, what the traffic class is for individual packets. If you want to use something like PFC, you have to somehow classify packets, manually into the traffic classes. But InfiniBand and PCI Express support that natively, and they also support flow control. So both InfiniBand and PCI Express use credit-based flow control, and you can only send as much data as you have, credit to send. For Ethernet, you can just send whatever you want, whenever you want, unless you receive a pause frame, then you got to stop for a while. The other thing is that InfiniBand and PCI Express are, intended for a hardware implementation. where software is not necessarily going to be touching or screwing around with the individual packets. The hardware is going to be responsible for generating it on the transmit end and peeling everything apart on the receive end. Versus Ethernet, for the most part, you're going to be handling stuff in software and then potentially accelerating a few pieces here and there with hardware. Probably the most important thing to take away from this are the fact that the payload length for InfiniBand does not include any variation in the header size. You can always send up to 4096 bytes, and the fact that it's a D-word based protocol, because that does add a couple of quirks to the wire protocol that you don't see in protocols intended for Ethernet. All right, so moving on to InfiniBand transport service types. So we discussed these very briefly last time. There are basically 5 of these. There's unreliable datagram, unreliable connection, reliable connection, extended reliable connection, and reliable datagram. So I'm going to go over all of these kind of at a high level over the next couple of slides here. All right, so the first transport service type is unreliable datagram. I'm not going through these in the same order that they are in the specification. I'm kind of building them up in terms of complexity. So hopefully that'll make things a little bit easier to understand. So unreliable datagram is basically just like UDP. It's a connectionless standard. So basically you can send, whenever you send an operation, you'll attach an address to it at that point. You don't, attach destination address when you open the connection. So, it's like in Ethernet, if you wanted to open a socket for TCP, you'd have to specify the address and whatnot then. And I think for UDP, you can also do something similar where you specify the address for every packet that you send. And this allows you to use a relatively small number of queue pairs for communicating, because you don't need to open up a queue pair for every destination you want to talk to, unlike a lot of the other transports. But similar to UDP, this doesn't provide any kind of guarantees for data delivery. It doesn't preserve ordering. It doesn't detect any errors or anything like that. If the packet arrives, it arrives. If it doesn't, it doesn't, and there's not much you can do about it. For unreliable datagram, the only operations supported are send and receive. So basically just like UDP, you can send a message, you can receive a message. That's about it. For unreliable datagram, everything is sent as a single packet. So any message you want to send has to fit into whatever the configured PMTU is, which is limited to 4096 bytes at the highest setting. So building on unreliable datagram, you have unreliable connection. So the idea here is to add some guarantees for data delivery. So with the unreliable connection, you have a one-to-one queue pair to queue pair connection. So for every other node you want to talk to, or for every other queue pair you want to talk to, you have to use, you have to allocate an additional queue pair. So this is kind of like, TCP. You open up a socket on one end, you have a socket on the other end, you connect them, and you can communicate. And you specify the destination address when you're setting up the queue pair, and then every operation you perform on that queue pair will be sent to the same destination. For UC, the idea is to use packet sequence numbers to detect dropped and reordered packets. And this provides some guarantees on data delivery, right? It's going to be able to detect duplication, reordering, and drop packets, and report errors. But it's not going to be able to really do any kind of error recovery, because it doesn't inform whatever's on the other end that an operation succeeded or failed or whatever. The operations supported by UC are send, receive, and write. So you can do RDMA writes over unreliable connection, but not reads. With UC, you can send much larger messages. You can send messages that can be split across multiple packets and up to 2 to the 31 bytes. So that's like what 2 gigabytes, I think, something like that. I don't necessarily think it's a good idea to send such a large block of data over UC. If you lose one packet, then the whole thing gets dropped, but it supports it. So just a quick note.
We have a couple of use cases for this is pretty useful, by the way.
Right. Yeah, I'm sure it's got a lot of use cases because it's simpler than RC and whatnot. But we can discuss that a little bit later. I mean, everything's in the spec for a reason. So if it's hard to use, if it has limitations, I mean, it's going to have some advantages to balance it out. So I'm just talking about how it works here, not so much what the differences are or what the advantages and disadvantages are. All right, so how does this work? Well, what happens with UC is all the TX packets, they contain a packet sequence number that's generated monotonically. So it's basically increments by 1 every packet that's sent. And then the receiver tracks the expected packet sequence number. So for UC, the first packet in a request is unconditionally accepted. So I'll talk a little bit later about how packets can be segmented or how requests can be segmented across multiple packets. But when the receiver sees the first packet in UC, it will unconditionally accept it and then update its expected packet sequence number to what it would expect after that packet. But if it sees any middle or last packets, it only accepts those if the PSN matches the expected PSN. So, if you send a request that comes in 3 packets and the middle one gets dropped, it won't accept the last packet because it'll see that as an out of order packet and it'll be dropped. And then if a new operation starts, then the first operation will be flushed out basically and reported, as an error, didn't complete correctly, and then, the new operation will take place. So that's just a kind of a high level overview of how UC works. So what if we wanted to make that a little bit more reliable? Well, this is where reliable connection comes in. So this is kind of similar to TCP because you have the sequence numbers and you can do retransmissions and timeouts and things like that. Again, still a one-to-one connection between queue pairs. It uses a packet sequence number to detect dropped and reordered packets, but then it also uses acknowledgements and retransmissions to recover from errors. So this provides kind of the strongest guarantees for data delivery. There's no duplication, it preserves ordering, and it allows you to recover from errors. This supports all of the major operations of InfiniBand. You can do send, receive, read, write, and atomic operations. And also, you can split messages across multiple packets up to 2 to 31 bytes. And because, drop packets, because you can recover from drop packets, then you can actually move this amount of data reliably, because if a piece is missing or you get some reordering, then the sender can just, retry. So how does this work? Well, just like UC, the TX packets contain a sequence number. On the receiver, packets are only accepted if the sequence number matches the expected sequence number. So if the sequence number is less than the expected one, then it's a duplicate packet. So there's ways of handling that. It either gets dropped or it's a retry of an operation that didn't succeed before. Otherwise, it's a packet sequence error, and that can be reported, and then not acknowledgement sent, and then the operation can be retried. Completed operations and errors are then reported with AX and NAX, and the requester can retry, failed operations. Pretty straightforward. The problem with RC is that it requires a lot of queue pairs for all of this communication when you have, lots of processes running across lots of nodes. So extended reliable connection uses what are called shared receive queues. So you can actually kind of amortize a particular, a single queue pair to queue pair connection across multiple processes on the destination. This provides all the same guarantees of data delivery as RC because it works exactly the same way. It just allows you to basically multiplex multiple connections through the same queue pair to queue pair connection. All right, and then finally we have RD and reliable datagram. The idea is to provide the same guarantees that that RC can provide, but again, without using as many queue pairs. So this is connectionless. Instead, you use these end-to-end context objects to track sequence numbers, and it provides strong guarantees of data delivery. And you can do all the same stuff as RC, but apparently nobody implements it. If Mellanox doesn't implement it, what's the point? So we don't need to think about that one too much. But if you wanted to implement that, there's a bunch of additional stuff that needs to be implemented in terms of, not only the software API, but also, the end-to-end contexts. And yeah, it's, well, if nobody else implements it, what's the point? All right. So that rounds out the different transport services that are provided. So what are the functions that can be sent or performed over these various transport services? And it boils down to send and receive, RDMA write, RDMA read, and atomic. So send and receive, we talked about this a little bit before. This is how you can send or push a block of data or data buffer or a message to another device in an InfiniBand network. So optionally, a send and receive can include immediate data, and a send is always paired with a receive. So on the receiving end, you have to queue up a buffer to receive the data that you're going to send. And potentially you would have to do some application specific coordinating to get this set up ahead of time. And send and receive are supported by all of the RDMA transports. This is kind of the simplest way, the most basic way to use RDMA or to use InfiniBand. And then we get into the RDMA operations. So read, write, and atomic are all kind of considered RDMA operations because they operate in the virtual address space at the destination. So RDMA write allows you to write a buffer or a block of data into the destination virtual address space. RDMA writes can optionally include immediate data, which consumes a completion queue entry at the receiver. If you don't do that, then it doesn't touch any work queue entries or completion queue entries at all at the receiver. It just kind of, the data just shows up. The software is completely unaware. When you send an RDMA write, you also need to provide the destination virtual address and the R key, and the application has to exchange this somehow. The InfiniBand spec doesn't talk about how to do that. You have to come up with something custom for your application, or use a library that can do it. So I think if you use like MPI or something, and you do MPI over RDMA, it handles this kind of stuff, in the background. But if you're going to work with RDMA directly, then you might need to do something to exchange this information. And this is supported in everything except UD. Right. And then we have RDMA read. Oops, there we go. So RDMA read is kind of the converse of RDMA write. It allows you to read a block of data from the destination virtual address space. And this requires a destination virtual address and an R key, same as RDMA write. Again, the application somehow has to exchange that information. With RDMA reads, same as RDMA write, doesn't consume any work queue entries or completion queue entries at the receiver, and it's supported in RC, XRC, and RD. Pretty straightforward. Let's see. And then we have atomic operations for anybody who's done any kind of multi-process, multi-threaded communication. You probably know why these are useful. So atomic operations over RDMA, it allows you to perform fetch, add, or compare and swap operations in the destination virtual address space. So these are the same as everywhere else. It performs a read and then does something and then writes a result back. So for fetch and add, it reads a piece of data, it then adds something to it and writes it back, but it does it in such a way that no other part of the system can affect that memory location until after that write takes place. And that includes nothing else is allowed to read that memory location until the write takes place. And so that way, if you have multiple entities trying to perform fetch and adds or compare and swaps on the same memory location, they're all going to take place separately in sequence. You're not going to have like two reads take place and then two writes, which kind of break what you're trying to do with fetch and add or compare and swap. So these are supported in RC, XRC, and RD. PCI Express actually supports atomic operations as well, but I'm not sure if Mellanox is taking advantage of that on their NICs. I've not done that. I've not used the atomic operations over PCI Express myself either. So something to potentially think about, if we're going to implement this, is to, look into using PCI Express atomic operations instead of whatever Mellanox is doing where they don't use those. But there's probably some advantages to not using PCI Express atomic operations. Not sure about that. That'll be something to think about at some point. Right, so another question is, what does all this look like on the actual wire? Right, so there's an excellent summary on page 170, figure 46 in the InfiniBand specification, and I can pull that up a little bit later if people want to take a look at it if you don't have a copy of the spec locally. It's actually not in the kind of transport specification part of the spec. It's in the data packet format, chapter 5. But anyway, it seems like they've described most of the header fields and whatnot twice in the specification for some reason. Not sure why. Doesn't make complete sense. Anyway, InfiniBand packets consist of a number of different pieces. So there's first the LRH, the local route header, and this is basically more or less equivalent to what an Ethernet header is for. It contains, local addressing information. And then you have a GRH, which is a global route header. In InfiniBand, this is optional. You may or may not need it. This is kind of similar to an IP header, right? It contains addresses that you can, configure on a, larger scale than the local identifiers used in the LRH. Then inside of the GRH, you have the BTH, which is the base transport header. And this one, describes the actual operation that's going to take place. So for Rocky, the BTH is kind of where everything starts. For Rocky v2, you don't see the LRH or the GRH. The packet data starts with the InfiniBand part starts with the BTH. The BTH header is then followed by several extension headers, which may or may not be present. It depends on the opcode in the BTH as to which combination of extension headers you're going to have. And there's a table in the InfiniBand specification that maps the opcode to all of the extension headers that are going to be present and in what order for that particular opcode. After the extension headers, you then have the actual packet payload. And then the payload is followed up by the ICRC and the VCRC. So the ICRC is basically equivalent to the TCP or UDP checksum. And then the VCRC is basically equivalent to the Ethernet FCS. So the ICRC, you compute that by the original sender and you check it at the receiver at the other end of the link. The VCRC, or not the other end of the link, the ultimate receiver that's going to be actually handling the data. The VCRC is just used to protect packets as they traverse individual links. And the reason you need both is because the VCRC doesn't protect you if bits get flipped inside of switch buffers or something as the packet is being sent. Same thing with the like the TCP checksum, right? Because the Ethernet FCS will protect you as the packets traverse the links, but if you get a bit flip inside of a switch buffer, then the Ethernet FCS is not going to help you. You need the the TCP checksum in order to detect that. So there's, like I said, there's a summary on page 170 of the IB specification that lays out all of the fields. All right, so I'm going to talk about these fields, these headers, just at a real high level here. So, like I said, the local route header, this contains virtual lane and service level information. Like I said, InfiniBand natively supports virtual lanes and traffic classes. So there are fields in the LRH for this. There's source and destination link identifiers, which, like I said, are basically more or less equivalent to MAC addresses. They're not, globally unique. They are assigned because they're like 16-bit numbers, but that's the idea with those. Then there's a packet length field. And this is only used in InfiniBand because this is part of the InfiniBand link layer. It's not used in Rocky or in Rocky v2. Inside of the LRH, you then have the GRH, and this one has another traffic class indication. It has a flow label, payload length, hop limit, which is basically the same as the TTL that you see in IP headers. And then it has the source and destination global identifiers, which are 128-bit fields. Presumably that's kind of the same idea as IPv6 addresses, more or less, for routing. The GRH is optional InfiniBand. If the local route header is sufficient, then you don't need the GRH. It's required in Rocky, and it's not used in Rocky v2. Just for reference. All right, so inside of the GRH, we have the BTH. So this one has several different fields that are required for the various transports. It has the opcode that indicates, what operation is being described here. And this is This is used for both, requests and for responses. So there are opcodes for, acknowledgements and RDMA read responses and things like that. But not for RDMA receives, because those don't actually go anywhere. um, then there's a pad count, right? So like I said, InfiniBand is a D-word based protocol. So you actually have to pad out the payload to a D-word multiple. So all the packet lengths in the LRH and whatnot are all in terms of D-words, not in terms of bytes. And the ICRC has to end up on a D-word alignment. So at some point, you're going to have to add between 0 and 3 padding bytes at the end of the payload. And well, there's a 2-bit field in the BTH that contains the number of padding bytes that you added. So you can actually recover, what the original payload looked like. Additionally, there's, partition key and destination queue pair numbers. There's some ECN bits for explicit congestion notification. There's also an acknowledge request bit that you can use for the requester to request the responder send an acknowledgement. And then there's finally a packet sequence number. So I talked a little bit before about how the packet sequence numbers are used in RC and UC, but that number sits in the BTH. Now inside of the BTH, you then have one or more extended, well, actually you could have zero or more extended transport headers. And the presence of these is determined by the opcode in the BTH. It's not like there's a bit field saying this header is present and this one is not present. Unfortunately, you have to just make that determination by looking at the opcode. So these carry a bunch of different pieces of information. So like the RD ETH contains the EE context identifier that's used for RD. For DETH, when you're sending datagrams, well, since you don't have a connection, you need to know the source queue pair. So, well, you send the queue key in the source queue pair for RD and UD. And then you have the RETH. This is for RDMA. This contains a virtual address, R key, and RDMA operation length. Just thinking about it right now, with an RDMA write, you have like 3 different length fields, right? There's one in the LRH, one in the BTH, and one in the RDMA extended transport header. So I don't know why you need so many length fields, but you definitely need the RDMA length field for reads. It's a little bit redundant for writes. Then you have the atomic extended transport header. This contains what you need for atomic operations, which is the same kind of thing. You have the virtual address R key, and then instead of length, you have the 2 operands for the compare and swap or the fetch and add. And then you have the ACK acknowledgement extended transport header. So this one gives you the ACK or NAC status, error code and a message sequence number. Then you have the atomic acknowledgement extended transport header. And this one includes the original remote data for atomic operations. So kind of the point behind fetch and add or compare and swap is that you read the original value, then you perform some operation and you write the new value back. Well, then the very important part is that you have to return that original data. So that's done in the atomic acknowledge extended transport header. Then there's another header for immediate values. If you do a send with immediate or write with immediate, that needs to be sent somewhere. And then there's also a transport header for the R key for invalidate operations, and there's another one for the XRC SRQ. When you're using XRC, you have to identify the destination SRQ number. So that's done with this additional extended transport header. So to be honest, this is not particularly complicated, but it is a little bit tedious. So, let's see. Now, the other thing is that IB has kind of some standard ways of segmenting operations across multiple packets. So if you look at the list of opcodes in the InfiniBand specification, you'll notice that there's 4 variations of a lot of them, right? There's only, first, middle, and last. So if you want to transfer 1 PMTU of data or less, then you can send an only packet, which indicates that that's the only packet that's in that request. Don't expect any more packets, and this is the first packet of the request. If you have 1 or 2 PMTUs, then you send 2 packets, right? You send a first packet and a last packet. So the first one is this is a new request, but there's going to be more packets. And the last is, okay, this terminates this request. If you have more than 2 PMTUs, then you use first, middle, and last. Pretty simple. The first and the only packets carry most of the operation-specific data. So if there's like a, an RDMA extended transport header that has the addresses and whatnot, that only goes in the first packet of the request. That's not duplicated across all the packets. And then the only or last packet are the only ones that can carry the immediate data. So if you do like send with immediate, the split across multiple packets, only the last one will have the immediate data in it. All request packets that, so basically all request packets carry routing information. So that's RDETH, DETH, XRC ETH. You need to know, what queue pair at the destination, to associate the request with, because you don't have this established connection. And then the first and the middle packets always carry a full PMTU of data. The only packet where you're allowed to send less than a full PMTU is, the last packet, or the only packet. If you're just sending one packet, then you don't need a whole PMTU. But for the first and the middle, you have to send a full PMTU. So if your PMTU is 4096, then every packet's going to have 4096 bytes of payload, except the last one. All right. So that about rounds out everything I wanted to say about InfiniBand. So that brings us to Rocky and Rocky V2. So Rocky, the idea is to replace the InfiniBand physical and link layers with Ethernet. And Rocky V2 extends that to replace the network layer with IP and UDP. So this is kind of a little summary of what this looks like. For InfiniBand, we have the InfiniBand network layer, the InfiniBand link layer, and then we have InfiniBand, network management. For Rocky, you replace the link layer with the Ethernet link layer, and then we use Ethernet management. You manage it just like you would an Ethernet network. And then for Rocky V2, the IB network layer, which is the GRH, is replaced with IP and UDP. Pretty straightforward. So what does this look like on the wire? Well, we have Rocky, we have Rocky V2. For Rocky V2, we have the Ethernet L2 header, we have the IP header, UDP header, and then the InfiniBand BTH and extension headers, followed by the InfiniBand payload and the ICRC. And then the Ethernet FCS takes the place of the InfiniBand VCRC. So the InfiniBand VCRCs are not used for Rocky or Rocky V2. And then presumably you may have some padding bytes in between the ICRC and the FCS for small frames. I think the headers are small enough to the point where you might need a few padding bytes. Not sure off the top of my head, but presumably you may need to insert a few padding bytes. And this ICRC here is always going to be, a multiple of 4 bytes from the start of the BTH header here. So actually, if you put this on 0, this is 14 bytes, so that's not D-word aligned, but this is going to be D-word aligned with respect to, the Ethernet payload. Right. Okay. I don't think I have anything else to say about the InfiniBand wire protocols and transport services and whatnot. Are there any questions about that? No? All right.
Something quick. You said
Sure.
that when there are errors, they're notificated. How do they? Are they notificated all the way up to the application? No.
So I think it's a little bit different for. Let's see, where are these done here? Okay, so UD
on UD
is not going to do anything. UC. So that the errors are not going to be propagated across the network for UC. So the only errors that are going to be reported are going to be reported, locally to, whatever is hosting the card. I'm not sure offhand exactly how the errors are reported, presumably in the completion queue entries, but there could be some other paths for error reporting. And I don't think it's necessarily going to report every possible error, right? Because if it doesn't see the start of an operation, then it can't really report that the operation failed.
I think the completions happen in different moments depending on the transport mode. So if you're on UC, I don't know exactly the moment, but the card doesn't necessarily need to wait for the peer card to say anything about receiving the packets for it to issue the completion. Whereas the same operation.
So I guess Right. So I guess you kind of need to separate out what's happening on the requester versus what's happening on the responder. So the requester is sending the request. With UC, as soon as the packets are sent, you get the notification saying it's done.
Right.
And then on the other end, well, yeah, and then with UC, when you get the request or when you get the completion saying it's done, that doesn't actually mean the operation was completed. It just means the operation was sent. It was issued.
Right.
Because
Now,
you don't have any feedback from the other end. And
on
then
the
on the receiver
receiver
end, as the packets arrive, if you miss the first packet for an operation, it's not going to inform you that the operation failed or was dropped or something like that. I think you're only going to get a notification, if you missed a packet in the middle of an operation, then you would probably get like a packet sequence error or something like that.
I see. I need to look
or
into
an
this.
indication that the operation failed because it started, but then it didn't see all the pieces. But if you miss the first packet, then you don't know what the request is. So, well,
If a packet arrives out of order, you're saying that it gets dropped.
Yeah. I'm not quite, right? Because let me go take a look at this next slide here, where I actually went to the spec and took a look at this because I was curious.
Yeah, that's what I was saying. Out of order
right,
packets are
so-
silently dropped.
Right. So out of order packets, this is out of order packets within a request, right? So if the request itself arrives out of order, as long as you see the first packet of the request, then it will be accepted. So the way UC works is that the first packet in a request is unconditionally accepted, right? So if the last packet of a request gets interchanged with the first packet of a subsequent request, then it will actually start that second request and kill the first one. That's what will happen in UC. So the first packet is unconditionally accepted, and then it will update the expected packet sequence number. So this is actually somewhat useful because you don't need to make sure that the PSNs on opposite ends of the link agree. It doesn't matter what the responder is set to, because the first request that you send will set the expected sequence number.
And you're saying there's no tolerance within which there isn't a reorder buffer.
No. I mean, at least that's not part of the InfiniBand specification. So it's possible you could implement one to improve the situation a little bit. But
no, I see. It's just that this doesn't match my expectations. That it's much more dangerous. Unreliable is much more unreliable than I thought.
Well, so RC is exactly the same. If something comes in out of order, you get a big honking error message saying packet sequence error, right? It doesn't accept it if it doesn't match the expected sequence number.
My expectations on RC, the acts that you're gonna get a NAC, and the cards are going to renegotiate a
Right.
transmission. And on the software layer, I wouldn't see anything. Maybe I'll pick up some weird latency, but if that, at least that's my expectation. I don't have much experience with errors. Unreliable reordering is something that happens pretty often in certain kinds of networking.
Right.
So this is, yeah.
Well, so that does become a consideration perhaps over, what kind of request size that you're sending, because if you keep everything within a single packet,
right.
it doesn't
Okay,
matter,
so
because then you're not going to have any reordering from the standpoint of UC.
So you're basically saying is like you're in danger when you a segmented scenario, but if you're not a segmented scenario, then and the PSN doesn't arrive in order, you have a hole in the PSN, and that hole basically arrives later. What you're saying is, if it's an only kind of operation, we're talking about the 4 different types,
right?
Then it's going to get accepted.
Right.
I see. That makes sense.
Yeah, I guess maybe I should modify what I said earlier about UC, because ordering is only guaranteed within each request. Ordering is not guaranteed across different requests.
Oh, because I use segmentation a lot because it's super convenient to lay out data in memory and then pad it to the MTU that you're using, and then just point a wookie to the whole thing, and just tell the card to dump whatever is it your huge data structure is, And if it's padded correctly, then you're going to get one element of your data structure in each packet. But I was kind of caught by surprise. It makes sense what you're saying is if there's a reordering in the middle of the thing, you're gonna lose the whole batch.
Yeah.
Got it.
So I think what will actually happen is that it's going to process the packets as they arrive, and it will actually start writing them out. But when it sees that reordering, it will abort and drop all of the remaining packets in the transfer. So you might actually end up with part of the data structure written into the destination, but you won't see how much.
This is bad. So UC supports write or no?
It supports RDMA write, but not RDMA read.
That's the thing. So you can basically corrupt your peer memory if something happens. Not corrupt. Oh, well, corrupt. Yes.
Yeah, it could end up in an inconsistent state. So
right, exactly. The peer application should know before touching data to. Anyway, interesting point. Very, very interesting point.
Right. I mean, this is where the RDMA write with immediate can be useful, because you won't get that immediate value if it didn't complete the operation. But at least that's for RDMA write anyway.
Yeah.
And then RC, it's more strict because it only accepts packets if the PSN
sure
matches.
Yeah.
If it doesn't match, it doesn't do any reordering, but it will send presumably, I take another look at the spec. Presumably it'll send a not acknowledged, and then that'll be followed up with the requester retrying the operation.
Right. Good stuff. Yeah.
All right, so that's all I got for the slides. So I'll go ahead and back out of that. All right, so let's see, what else do we need to discuss for today? Let's see. Well, we don't have too many people, so I guess it doesn't make sense to try to put people on the spot about potentially working on various subsystems. Yeah, I know I got your email about potentially working on the memory management stuff,
Yeah,
right? And the protection domains and whatnot.
PD and QP, yeah. At some point, if it's useful, like I told you, Xilinx has an embedded RDMA IP with some interesting. It's interesting to look at the architecture. We may, select the portions that we like and kind of redesign the portions we don't like about it.
Right. Yeah, I've actually taken a look at the Xilinx ERNIC IP just to kind of get an idea of how it's put together. Because if you're going to start a big project, it makes sense to take a look at existing projects and existing devices just to get a feel for how are these things usually put together. So it's like when I was working on Corundum, I spent a very long time looking at the Mellanox device driver source code just to figure out how do you make a high performance NIC, right? What do you need to do? The Mellanox NIC runs fast, so if we do something similar, it'll probably be fast. So with the Xilinx ERNIC, that's definitely something to take a look at. I don't know about actually looking at running it, but there's definitely a lot that you can glean from the documentation. The other thing about the ERNIC is it's designed to be embedded. I mean, I think that's what the E is for, right? Embedded RDMA NIC.
Right. There's no memory. There's no memory. The memory infrastructure is not there.
Right. So it's a slightly different configuration, which is perfectly fine. I mean, as I was looking at that, I'm like, I could definitely see the use case for kind of an embedded device. And with Corundum, eventually what I want to be able to do with it is run it on things like SOCs and whatnot. So that's kind of one of the motivating factors between this kind of phase 2, phase 3 split in terms of, how we're putting this together. Because if we can make kind of the first version of this a little bit like an embedded, stack, we can kind of keep that functionality around so that if you don't, want to deal with caching of some of the state information, or you don't have a host with a bunch of DRAM, then you can turn that off and run, completely, within the FPGA, which for certain applications could be, a significant advantage. I mean, that's another thing about like that HLS stack for Rocky, right? Because that's also an embedded stack. So you wouldn't necessarily want to put that on a NIC, but if you want to have two applications talking to each other on two FPGAs, yeah, it could make some sense. I know we were talking about segmentation. I have no idea how those guys handle segmentation. Well, I guess if you're forcing no. Yeah, I'm not sure what they do. They must be very limited in terms of, how much stuff they can put back together because of
the interesting thing, you can
FPGA
control
resources.
it. You control it. If you don't want, if the application doesn't want it to happen, it can, which is interesting.
Right.
Yeah.
Right. Yeah.
Their NIC is interesting. Yeah, it simplifies the memory, but it could be interesting to learn how they manage a Q-pair state. I think mostly
right. So I think with the Xilinx one, they basically just store everything directly in block RAM, basically. So all the Q-pair state is just all directly in block RAM. So you're very limited in terms of how many Q-pairs you can open up on that. You can't open up an arbitrary number that supports like 128 or 256 Q-pairs or something like that. And then everything just sits in block RAM. So for kind of the phase 2 functionality for Corundum, that's kind of what I'm thinking is going to make sense, right? Just toss everything in block RAM. And then for phase 3, then we can try to figure out, okay, is there a way to, cache things in block RAM, but kick out the active state or the, inactive state into DRAM of some sort, either on the card or on the host. And that'll allow you to support, a lot more Q pairs. But it does add a lot more complexity. So the hope is we can implement everything on the FPGA first and get, a lot of the kinks worked out of it and, get to a point where, things are functional. And then we can look at, kind of extending the scalability and extending the capabilities. That's kind of how I've developed Corundum up until now anyway. It's like, let's get something working, let's figure out where the bottlenecks are, and then go rework it. It's gone through, at least kind of 2 major architectural overhauls and major rewrites up until now. And, for this, we're going to be doing at least a third and possibly more. So I was just thinking about this a couple of days ago that we're basically going to be, at least part of implementing the phase 1 functionality, we're basically going to be rewriting most of Corundum, which is not necessarily a problem, but we can do that incrementally. So we're not starting from scratch.
Absolutely agree. Yep, incremental is the way to go.
Yeah, and I know you're also talking about potentially peeling off kind of the core logic of Corundum into a separate file. I've been taking a look at what it might take to do that, and there's a few loose ends I got to get tied off, but it's looking like that's going to be a very doable thing to do, and that should make it a lot easier to port to other designs, because you just have the the core logic you drop down, and then you connect the device specific stuff, and then it's also going to make it easier to add features, because you won't need to edit the same stuff across a whole bunch of different files, because it'll just be the core logic, and then that'll be run across all the different designs. So looking into how to do that, the issue is in terms of all the control registers and whatnot, right? For boards, you're going to need to implement potentially some board specific registers for, talking to optical module control lines and firmware updates and things like that. So I need a kind of a nice way of overriding some registers from a higher hierarchy level. So haven't quite gotten my hands completely, or my head completely wrapped around that, but I got some ideas. So
that'll be interesting. The question there, is there any board where you use DRAM at all?
Right now, no.
Yeah, so you basically, and which is super nice, because you have 2 IPs, two flavors of each IP depending on the board and then the whole core logic. But speaking about caching, yeah, I don't know if you can. I don't know if at some point it would be interesting to reach out to this kind of resource, if the resource is there, and then it'll be an extra IP. And if you go in that direction, I don't know. You mentioned at some point that you like the Zinc platform as well. We like the Zinc platform for a few things as well. It's a whole other beast. How do you how not to get into a nightmare of a continuous integration, continuous testing thing. But it's just a matter of, like you're saying, of being aware and refactoring the design and moving things to a core design that's independent of the platform as much as possible.
Right. Yeah. Speaking of Zincs, I actually have one of the boards that we're putting together for the research project. Early revision of it, but this has a little Zinc SOM on it, and the plan is to run Corundum on that for time synchronization purposes. So that's what I need to run Corundum on Zinc for. Basically just for PTP. Potentially there's some other solutions for that, but it's a good motivator to make that work.
Which Zinc it is?
So these are these little Trends electric modules here. What part is on here anyway?
Is it a 7000?
ZU4CG. ZU4CG. Zinc Ultra Scale.
Ultra Scale.
Yeah. Yeah. So these, well, we had to get these because we wanted 10 gigabit Ethernet connections, right? And the 7 series ones, it's actually quite hard to find a 7 series part that has 10G capable SerDes on it. There's not very many of them to begin with, and 2, it's highly dependent on the package. So you can actually find SOMs that have what looks like it might be the right part, but in the wrong package. So it doesn't support the full 10G line rate. So I spent quite a bit of time looking for that. It didn't really turn up much, but these SOMs support that. So it's like, all right, we'll go that route. I don't really feel like soldering a BGA, but a SOM, that's a little bit more reasonable.
Fair enough, yeah.
But yeah, I know there's some other people that have interest in running Corundum on Zincs of various descriptions. So that functionality will come at some point. There's a few pieces that are needed for that. One of them is the DMA components that speak AXI, and we're going to need those anyway for talking to the DRAM for the main design. So I'm not sure which one is going to come first. And then obviously we need to work on all the driver stuff to make that run on the Zinc and run under Peta Linux and whatnot. So
it may complicate. It may add 1 or 2 clock domains as well, which complicates things. The PS is very specific about clocks to talk to or clocks that you use to talk out of it. So it may. Those are things to pay attention.
Right. I seem to remember that all of the AXI interfaces, you can supply your own clock to those guys, and you can actually run at a relatively high frequency. But I'll take another look at that. Yeah, it's a good point.
We got bitten by it on the 7000. I don't know the Ultra Scale Plus.
Yeah,
I think you get
the Ultra Scale ones are a little bit more flexible.
You ended up needing to deal with a lot of cross-domain clocking and some pretty nasty bugs that come with, I was told.
Interesting.
But again, this is the 7000.
Right, yeah. It might be a slightly different story on Ultra Scale, but well, I guess we'll just have to see what it looks like. I'll take another look at the data sheet. It looks like that we can run most of the interfaces with our own clocks, at least on the AXI side, but we'll see. Well, we're gonna have to deal with multiple clock domains anyway, because all of the DRAM interfaces are gonna be running in their own clock domain. So I'm gonna have to make an AXI FIFO for that, asynchronous FIFO for interfacing with the DRAM and whatnot, which, not the end of the world, but it's another thing I got to write. So I have a synchronous AXI FIFO, so adapting that to an asynchronous one is not that big of a deal, but these things take some time. So but yeah, so that'll be the idea, and run the whole design in the PCI Express user clock domain and then bridge the gap into the DRAM clock domains. But I guess I also need to take a look at the width, because if the DRAM clock is faster, then we might want to run that with a width converter or something. And I don't think the performance of my width converter is very good right now. I'll have to take a look at that too. Lots of things on the to-do list. What's new? All right. let's see. Well, in terms of status, in terms of what I've been working on, I guess hopefully people have been watching on the Slack. But what I've been working on over the past couple of weeks is to try to get the generic PCI Express DMA interface operational. So this is a step towards more device support. So with the Intel devices, they have a very different PCI Express interface. So in order to make it easy to run, or well, easier to run with both that and what's available on the Xilinx devices, what I decided to do is to rewrite the PCI Express DMA engine to support a more generic PCI Express interface, and then we'll write shims that adapt to whatever the device specific interface looks like. So I have shims for UltraScale Plus, 7 series devices. They all use the same kind of PCI Express interface that adapt that to the generic interface that I put together. And the generic interface is very similar to the Intel P-Tile interface. So that'll make it easier to run on the P-Tile devices, which are Stratix 10DX and Agilex. But I'm also going to write shims for the Stratix 10 MX and hopefully a RIA 10, because it's the Stratix 10 MX that we're going to be running at Sandia in the testbed. And for a RIA 10, I also just recently received a whole stack of these little ARIA 10 dev boards. So these are made by a company called Guidel or Guidel. Not sure what the proper pronunciation is, but this has an ARIA 10 FPGA on here, a pair of SFP pluses, and PCIe Gen 3 by 8. I got 20 of these, well, 19 of these. So what I want to do, hopefully, is provide them to people that are interested in working on Corundum, but otherwise can't get a hold of FPGAs. Although there are some downsides to these. They don't have USB JTAG, so I'll have to sort that out one way or another. And you need, cordless licenses in order to target these. But they are ARIA 10s, which are reasonably modern, so less of a concern than trying to run on a Stratix 5 like on these. I think there was some discussion about, getting it to run on these, Catapult FPGA boards, but the Stratix 5 on here are getting a little bit long in the tooth. So my main concern with these is, timing closure, how hard is it going to be to make things run? And it's yet another PCI Express interface. Both the generic interface does make that a little bit easier. So some things to think about going forward. Let's see. Yeah, there's really not too many people on here. Otherwise, I would try to poke a few more people. But yeah, I guess I'll have to send some mails around to the list about, seeing who wants to work on, what subsystem. But yeah, I mean, the thing to keep in mind with the subsystems is that, I don't have the time to do, the detailed design work going all the way down to the individual Verilog modules and then saying, hey, you work on this module, you work on that module, whatever. I would like to do that so that, people can start out with relatively simple things, but, I'm working on the phase 1 features. I got my own things to do. But this is a really good opportunity for people that, want to sink their teeth into a big complicated project, right? It takes some time to get your head wrapped around, how to pick something apart into small pieces so you can actually implement it. So I'm hoping that we'll be able to find some people that have the time to step up to the plate and help make that happen. So seems like Alberto, you're willing to do that for the memory management stuff, which I think is going to be super useful. Hopefully we can find a few more people. So in terms of, how complicated the various subsystems are, I think the memory management one is probably going to be the most annoying from a scalability standpoint. First, right? Because, a couple hundred memory regions is not all that much. A couple hundred Q pairs is, quite a bit, I would think, for a lot of applications. So we're definitely have to think about how to make the memory management stuff more scalable. But for the number of Q pairs and whatnot, I think that can be a slightly longer term thing to figure out how to make that more scalable, which makes things a little bit simpler.
Agreed. Yeah. Yeah.
All right. Is there much of anything else that we need to talk about? I think that about rounds it out. I got my slides. I guess for next week, we'll have to figure out who's going to talk about what. Would you want to talk about the memory management side of
I want
RDMA,
to.
or
I don't think I can get to memory management. So I was curious about.
maybe not for next week, or for not for next for 2 weeks from
No,
now.
for the next meeting, I'm sure the next 2 weeks there's a bunch of stuff, trips. But maybe the meeting after that, I wouldn't start by memory though. I would look into the Q pair state if you think that's also useful. And I was thinking of picking apart the RNIC and seeing.
Right, the Xilinx Yarnic, yeah.
I mean, just get a look at a design and expose the design, and maybe we can pick it apart, and we like this, we don't like that. But this is definitely not going to happen for the next one. Maybe the following.
Yeah, that's true. Yeah. All right. Well, all right. I guess I'll have to figure out something for the next meeting as well then. Oh, well, it is what it is. Hopefully we can get some more people involved as opposed to just passively listening, which, nothing wrong with passively listening in, but it's not going to get built with people just listening, right? All right. Well, I guess I don't have too much to add for today, so I guess we'll sign off for now then. Thanks to all you guys for listening in.
All right, thanks a lot. That was a good presentation, actually, and I actually learned a lot about RDMA, I guess.
Well,
so if I'm going to contribute, I'll have a lot to practice and study.
Well, I mean, that's kind of the point with these little presentations, is I want to, try to get people up to speed with the RDMA that aren't necessarily up to speed. So, but it also doesn't help that I'm not very familiar with RDMA. So I'm hoping that what we'll be able to do is, have different people kind of cover, different topics, and part of the exercise will be, actually putting together the presentation, not just listening to presentations. So I'm not sure if you're interested enough to, put together a little talk for one of these meetings, but if so, that would be great.
Maybe at some point after.
Maybe at some point. All right.
At some point. Okay. Well, thanks a lot again for today.
Well, and thanks for tuning in.
And next one will be in 2 weeks.
In 2 weeks, yeah. I sent around a calendar invite to hopefully resolve any ambiguities. I'm also going to make sure going forward to send around a reminder email beforehand for people that maybe don't use Google Calendar or something.
Okay, cool.
Is there any definite plan for getting this rolled out? Or is it
What did you say?
Is there any definite plan to roll this out, or is it like this part of the RDMA?
Any definite plan to roll out what? The RDMA functionality in Corundum?
Yeah.
Well, I mean, so I guess we kind of discussed this in the previous couple of meetings, but so the functionality that we're trying to implement in Corundum going forward are kind of divided into a couple of different pieces, right? So I don't know if you've taken a look at some of the wiki pages on the Corundum GitHub repository, but I have a page on kind of the future of Corundum, and it kind of boils down to a couple of main things. Ultimately, what we want to do is turn Corundum into a platform for in-network computing that supports RDMA. But to develop this, I've kind of divided it into two pieces. One of them is RDMA support, and the second piece is basically everything else. So for the research that we're working on, I don't actually need RDMA support, but I do need a lot of the other capabilities. So what I'm going to be working on is everything other than RDMA. And then I'm going to be trying to coordinate, people in the community to, help develop RDMA, because, I don't have time to do it myself. If we can find some people in the community to help build that, that's great for me. That's great for the project. It helps build the community. And it's also, you know, in some sense, a learning experience for, you know, people that want to help. You know, you learn about, you know, how RDMA works on a very intimate level and how to work with, you know, these big complex FPGA projects. And, you know, I'm more than willing to make myself available to, you know, help get issues figured out and whatnot. I'm tied up with all of the phase 1 functionality to, you know, help implement the phase 2 and phase 3 stuff. So, you know, if nobody helps, then, you know, maybe in a year or two, I'll get around to implementing it myself. But hopefully we'll be able to, you know, get the project off the ground. So are you interested in using this functionality, or are you potentially interested in, you know, helping to build it? Just out of curiosity.
Yeah, so basically I do verification background. So as such, I'm not worked on the design side for a very long time. So
okay, so you're interested in the verification.
Yeah,
and the
but
testing.
I think I'll also start looking into the different subsystems which you ported on the GitHub and see like what interests me, and probably I'll talk to you on that.
Yeah, I mean, for verification, you know, depending on what you're interested in, there's a lot of code right now that either doesn't have test benches or potentially doesn't have a lot of test cases. I know I know there's a lot of interest in like formal verification. Potentially, you know, I've not done any of that myself. If that's something you're interested in, you know, you can definitely pick some modules in Corundum and formally verify them. You know, I'm not going to talk you out of doing that because that would be useful. But one thing to keep in mind is that some of the modules in Corundum are, you know, going away. They're going to be rewritten. So before you, you know, spend time like formally verifying the queue management logic, well, it might make sense to ask and make sure that that module is going to be sticking around before you spend too much time on that. But yeah, if that's something you want to do, you know, great. That could definitely be a good project for somebody that likes verification, but doesn't necessarily want to, you know, dive into, you know, all the details of RDMA and whatnot. It's just to take existing modules and, you know, write more comprehensive tests for them. So it's all based on what you want to do. I mean,
Correct. Yeah, I mean,
and what
touched
you
the
have
design
time
very
for.
long time ago, so it will be interesting. Like if I can pick up something.
Yeah, sure. Well, I mean, there's also the Slack and the mailing list, so feel free to post questions or get in contact with me if you want to work on some more stuff. So, and
Okay.
thanks for tuning into the meeting.
Yeah, thanks a lot. Yeah.
All right.
Okay.
Anybody else have anything to add, or I guess if not, then we'll go ahead and close things down for today.
Okay.
No, going once, going twice. All right. See you guys in 2 weeks then, or on Slack.